GATE 2021 Civil Engineering Set 2 Question 12. The ratio of momentum correction factor to the energy correction factor for a laminar flow in a pipe is option A is 1 by 2, option B is 2 by 3, and option C is 1, and option D is 3 by 2. Reference to the relevant NPTEL courses or video has been cited. Now coming to useful data for laminar flow through pipe, here we have two correction factor. The first one is momentum correction factor and the second one is kinetic energy correction factor. Momentum correction factor is beta and kinetic energy correction factor is alpha. Now talking about beta first, let's suppose we have a pipe whose radius is r and the laminar flow is moving, we can say, with a velocity u. So if we can take the projection of the pipe like this way and we have taken a small area inside, let's say this radius is dr and the inner radius is small r and the outer radius is capital R. So now the laminar flow through a circular pipe can be written as the velocity u will be minus 1 upon 4 pi del p upon del x into r square minus small r square. That can also be written as u equal to u max into 1 minus small r square by capital R square. U max for a laminar flow is u bar into 2, where u bar is mean velocity. These are the standard results or formula, we can say, which we'll be using to find out momentum correction factor and the kinetic energy correction factor. Now talking about beta first. Beta for a circular pipe is momentum per second based on actual velocity divided by momentum per second across the section based on mean velocity. So we know that momentum is equals to mass into velocity, and where mass will be the total mass of fluid flowing. So if you write it, that will be 2 pi r into dr into velocity. So if you put it in the equation, we will get beta equal to integration 0 to r rho into 2 pi r into dr into u into u, where this is the mass of the fluid and this is the velocity, and in upon that will be rho into pi r square into u bar into u bar. So if you solve this, we will get 2 by r square integration 0 to r u square into small r into dr divided by u bar square. Now if you further solve it, we can write it like this also: 0 to r u max square into 1 minus r square by r square into r dr divided by u max by 2 the whole square. Now if you further solve it, beta can be written as 8 upon r square integration 0 to r 1 minus small r square by capital R square into r dr. Now solving it, 8 by r square integration 0 to r 1 plus r की power 4 divided by r की power 4 minus 2r square divided by r square into r dr. Now if you solve it, we will get 8 by r square into r square by 2 plus r power 6 divided by 6r4 minus 2 की power 4 into r की power 4 r square. Now if you take the r square outside, this will be 8 into r square by r square. It will be 1 by 2 plus 1 by 6 minus 1 by 2. So 1 by 2 will be 0, and this will be 8 into 1 by 6, so that is 1.33. So beta for laminar flow is 1.33. Same like that, the kinetic energy correction factor alpha will be kinetic energy per across the section based on actual velocity. This will be based on u, and kinetic energy per second across the section based on mean velocity, that is u bar. Now if you put it in the equation, that will be alpha equal to integration 0 to r half mv square. So here mass will be rho into 2 pi r into dr into u square upon half into rho into pi r square into u bar square. Now if you solve it, we will get 16 upon r square integration 0 to r 1 minus small r square capital R square whole cube into r dr. Now if we solve it, we will get 16 upon r square integration 0 to r 1 plus r power 4 divided by r power 4 minus 2 small r square divided by capital R square minus small r square divided by capital R square minus r power 6 divided by capital R power 6 plus 2 small r4 divided by capital R power 4 into r dr. Now if we integrate it, we will get 16 upon r square into r square by 2 plus 3 upon r power 4 into r power 6 divided by 6 minus 3 upon r square into small r power 4 minus r power 8 divided by 8 into capital R power 6, and the limit is 0 to R. See, if we put the limit capital R here, we can take the R square outside. So this will be 16 into R square divided by R square. So the equation which we get is 1 by 2 plus 1 by 2 minus 3 by 4 and minus 1 by 8. So R square will be R square will be cut. The value we are getting here is 2. So our kinetic energy correction factor alpha is 2. So now coming to the video solution part, so the correction factor which we have got, the first one is momentum correction factor, which is beta, that is 8 by 6 for a laminar flow through a pipe, which we can write as 4 by 3. And the second one is kinetic energy correction factor alpha, that is 2. So now we are asked to find out ratio of momentum correction factor to kinetic energy correction factor, that is beta upon alpha. So we can write it like that, 4 by 3 divided by 2, that is 2 by 3. So 2 by 3 will be our answer. So the ratio of momentum correction factor to the energy correction factor for a laminar flow in a pipe is 2 by 3. Reference to the relevant NPTEL courses or video has been cited.